Let's look at OpenStax University Physics Volume 2, Chapter 14, Problem 31. A coil of 40 turns is wrapped around a long solenoid of cross-sectional area 7.5 times 10 to the negative 3 square meters. The solenoid is 0.5 meters long and has 500 turns. A. What is the mutual inductance of the system? B. The outer coil is replaced by a coil of 40 turns whose radius is 3 times that of the solenoid. What is the mutual inductance of this configuration? So before we write down the knowns and unknowns, I want us to look at the diagram. So we have a solenoid, and that's this thing, and I just chose a direction of a current for the solenoid. And around the solenoid there is a loop of wire, a coil that is wrapped right around the solenoid. So they basically have the same cross-sectional area. In part B, now we still have the solenoid, but the coil is this far out. So the coil has 3 times the radius of the solenoid. Now the problem is not very clear. I assumed that what they're saying is that the solenoid has a current going through it, so the solenoid would be the primary and the coil will be the secondary. So that's why I drew current in the solenoid. So it basically comes out at us, goes in, out, in a three-dimensional pattern here. So the difference between part A and part B is that this radius is larger. Now let's look at one more thing before we move on to knowns and unknowns, and that is the magnetic field that's produced by a solenoid. So we know that the magnetic field is inside the solenoid, and if this were the correct direction for the current, then the magnetic field would be to the right. I don't know, the problem doesn't tell us that, and it's not relevant for this problem. So since the magnetic field is inside the solenoid and the coil is wrapped around the solenoid, then this is the magnetic field that is inside the coil as well. In this part, we have the same situation where the magnetic field is inside the solenoid, but now the coil is farther away. So now that we know what the setup is like, let's write down the knowns and unknowns. I'm going to call everything related to the solenoid the primary and everything pertaining to the coil the secondary. So I have the number of turns in the coil, that would be number of turns of the secondary is 40. We know that the solenoid has a cross-sectional area of 7.5, so A primary is 7.5 times 10 to the negative 3 square meters, and actually this cross-sectional area is the same here for the solenoid and for the coil itself. Then we know that the solenoid is 0.5 meters long, and the number of turns of the solenoid, so that's the primary, is 500. In part A, we're looking for the mutual inductance. In part B, we want also the mutual inductance, but this time we have R of the secondary being 3 times R of the primary. All right. So let's write down the equation for mutual inductance. So mutual inductance is number of turns of the secondary times flux through the secondary divided by the current in the primary. We don't know the current. Let's just keep going and see what happens here. So looking at the diagram here, the number of turns of the secondary, that's fairly straightforward, 40. The flux through the secondary is magnetic field times area. Magnetic field is a magnetic field inside the solenoid, so caused by the solenoid, and the area is the area of the solenoid. So this will be number of turns secondary times magnetic flux caused by the primary going through the area of the secondary, which will be the same as the area of the primary, cosine of the angle between the direction of the area vector, which is in this direction, and the magnetic field. So that would be cosine 0, divided by the current in the primary. Now, since the solenoid is the primary, then the magnetic field that the primary creates is mu naught, number of turns per length, times the current in the primary, and then we multiply this by the area of the secondary divided by the current in the primary. So I said earlier, we don't know the current in the primary. Well, it doesn't matter. If you don't have a certain quantity given, it's possible that later on it will cancel out. So we don't actually need the current in the primary. So now the mutual inductance is going to be number of turns in the secondary, mu naught. Lowercase n is number of turns primary divided by the length of the primary. And we multiply that by the area of the secondary, which here coincides with the area of the primary. So we know all of these things. Plug in the numbers, so it's 40 times 4 pi times 10 to the negative 7 Tesla meters per amps, times 500 divided by 0.50 meters. And the area is 7.5 times 10 to the negative 3 square meters. And we get a mutual inductance of 3.8 times 10 to the negative 4 henries. So that was part A. Now in part B, we start out again with the equation for the mutual inductance. So it's number of turns secondary, flux through the secondary divided by current in the primary. So that is number of turns in the secondary, magnetic field caused by the primary times the area secondary cosine 0 divided by the current in the primary. So this is number of turns secondary times magnetic field, which is mu naught n I primary area secondary divided by current in the primary, and I primary cancels out again. And now we have to pay attention to something. So here I said that the magnetic field is only inside the solenoid. So the flux has to do with the product between the magnetic field and the area. There is no magnetic field going through here. There is no magnetic field going through there. So while I would have to take the area of the secondary, the area of the coil, I would multiply this much of the area by 0 magnetic field, this much of the area by 0 magnetic field. So all I'm left with is the area of the solenoid times the magnetic field. So then the mutual inductance will be number of turns in the secondary, mu naught, number of turns primary divided by the length of the solenoid times the area of the primary, the area of the solenoid. And when we plug in the numbers, we actually notice that we have the same equation here as we have there. So we'll still get 3.8 times 10 to the negative 4 Henry.